All right, let's talk about 1.7 inverse trig functions. You may recall from past math classes, from the past trig class perhaps, that none of the trig functions are one-to-one. So that means that they don't have proper inverses, right? One way to think about whether or not a function is one-to-one, I mean, we've talked about inverse functions already in this class, but remember that a one-to-one function has to pass the horizontal line test, and none of the trig functions do. If you think about the graphs of these things, like sine and cosine are just these waves, right? And so they fail the horizontal line test pretty miserably. Tangent and cotangent are a bunch of almost cubic-looking curves, but it's just a repeat, right? They're periodic. And sine and cosine are a bunch of almost parabola-looking things, but again, they're periodic, and so they're not one-to-one, and therefore they don't have inverses. However, you may also recall that what we can do is we can restrict the domains of each of the trig functions so that the trig functions are one-to-one on their restricted domains. And we choose particular ones that we just sort of take on convention, right, as being sort of like the standard restrictions that we make to the trig functions. And page 57 of your textbook has a good picture of these things. So the sine function, for example, the standard domain restriction that we make is that we require x to be between negative pi over 2 and pi over 2. And when you do that, you get just this little snip of the sine function. But what you'll notice is that it gives you all of the possible output values of the sine function, but it does so without any repeats. Okay? For cosine, if we were to restrict between negative pi over 2 and pi over 2, well, for one thing, we wouldn't get a function that's one-to-one, right? It would fail the horizontal line test. And for another thing, it wouldn't give you all the possible output values of cosine. It would only give you the outputs between 0 and 1, right? 1 and 0. It wouldn't give you any of these things. So for cosine, we have to snip it in a different place. So we snip it from 0 to pi. And that way, once again, we get all of the possible output values, but without any repeats. Okay. In a similar way, right? So here's the restriction for the tangent function, and then here's the restriction for the secant function. So we do the right half of the parabola that opens up, and the left half of the parabola that opens down, right? So we go basically from 0 to pi, except that there's an asymptote at pi over 2. So x is between 0 and pi, except at pi over 2. Now, your book doesn't list these restrictions for cotangent and cosecant. So I'll just tell you kind of verbally, for cotangent, we restrict between 0 and pi. And for cosecant, we restrict between negative pi over 2 and pi over 2, except that the cosecant function has an asymptote at 0. So we restrict between negative pi over 2 and pi over 2, except for at 0, right? Anyway, so these are the trig functions with their restricted domains. Now, the inverse of these things, of each of these functions, occurs when we take the points that are on the original and we swap the coordinates. So instead of the point pi over 2, 1 being on the graph of sine, well, pi over 2, 1 is on the graph of sine, but what that means is that 1 pi over 2 is on the graph of sine inverse. Okay? So down here, so here you have the original trig functions, right? And then down here you have their corresponding inverses. Okay? And functions and their inverses are symmetric with respect to the line y equals x. So if you imagine, drawing the line y equals x, and then flipping this function over that line, you get this one. And the same thing here, and here, and here. Okay? So anyway, this is page 57 of your textbook. I think it's a really good graphic for you to understand the inverse trig functions really well. Page 58 also has some good stuff on it visually. So it's a chart, and we'll come back to this chart here in a second. But that's also good information to help you make sense of all this inverse trig stuff. So in words, here's what we can say, right? Sine inverse of y equals x means that sine of x equals y, right? So you're swapping those two things, right? So sine inverse of y equals x means that sine of x equals y, and that x is between negative pi over 2 and pi over 2. Right? Cosine inverse of y equals x means that cosine x equals y, and that x is between 0 and pi. All right? And so forth for the others. I'm not going to read them all to you. You can kind of pause it and read them, write them down if you want to. But what I want to do is walk you through some examples. Okay? And again, for some of you, this is old information, right? Like you've been dealing with inverse trig functions, for a while now. But for others of you, this may be new. So let's just practice. Let's find the following without a calculator. So let's do sine inverse of 1/2. Okay? So sine inverse of 1/2. That means that sine of some value x equals 1/2. So we're looking for some angle such that sine of that angle is equal to 1/2, and the angle has to be between negative pi over 2 and pi over 2. So can we think of it? Can we think of what value makes sine equal to 1/2? So if you have the unit circle that I attached to the previous module in front of you, or if you have the values memorized, then you know that sine of 30 degrees, or pi over 6 radians, is equal to 1/2, and pi over 6 is between negative pi over 2 and pi over 2. So sine inverse of 1/2 should be pi over 6. Okay. You can use your calculator to verify this, but I want you to practice kind of doing this in your head so that you're really comfortable with the inverse trig functions and so that you understand them really well. But yeah, sine inverse of 1/2 should be pi over 6. What I want to point out to you is that this restriction is very important, because without this restriction, you would have infinitely many possibilities here, right? Because sine of pi over 6 is 1/2, but sine of 5 pi over 6 is also 1/2. Right? And sine of negative 7 pi over 6 is also 1/2. And sine of negative 11 pi over 6 is also 1/2, right? And we could keep going all day, right? There are infinitely many values here such that sine of that value is equal to 1/2. But only one of them lives between negative pi over 2 and pi over 2. Right? And the one that lives in the correct region is pi over 6. Okay, so that's why sine inverse of 1/2 is pi over 6 and not 5 pi over 6, for example. 5 pi over 6 is more than pi over 2. Let's do another one. So let's do sine inverse of negative 1/2. This is maybe a little bit boring considering that we just did sine inverse of 1/2. But let's think through it. So sine inverse of negative 1/2. That would mean that sine x has to be negative 1/2, and that x has to be between negative pi over 2 and pi over 2. What value is going to do the trick there? Well, there are a whole bunch of values such that sine of that value is equal to negative 1/2. For example, sine of 7 pi over 6 is negative 1/2. The problem with 7 pi over 6 is that it doesn't live within this region. Okay. By the same token, sine of 11 pi over 6 is equal to negative 1/2, but 11 pi over 6 is not in here. What is in here would be negative pi over 6. Sine of negative pi over 6 is equal to negative 1/2. And negative pi over 6 lives within this interval. So sine inverse of negative 1/2 is negative pi over 6. Okay. This, of course, requires you to know the unit circle pretty well, right? To have some exposure to the trig functions. And so if you need to spend some time reviewing that information, then spend the time necessary to review that information, right? But this isn't a trig class. I mean, we're assuming that you know this stuff, okay? And I'm just kind of trying to refresh your memory a little bit. Let's do cosine inverse of 1 over root 2. Now, some of you may be more accustomed to seeing this in its rationalized form. So if you rationalize 1 over root 2, you get root 2 over 2. And on the unit circle that I gave you, that's how they're listed. They're listed in their rationalized forms, not their unrationalized forms. So again, you might be more accustomed to seeing it this way. But we're looking for cosine inverse of root 2 over 2. This means that we need cosine of some value to equal root 2 over 2. And, now careful, the restriction is different. For cosine, the restriction is 0 to pi. Right? So x has to be somewhere between 0 and pi. So in this case, I think the value that will do the trick, cosine, I think it should be pi over 4. Cosine of pi over 4 is equal to root 2 over 2, and pi over 4 is between 0 and pi. Okay. Now just contrast that with cosine inverse of negative 1 over root 2, which, by the way, is the same as cosine inverse of negative root 2 over 2. This means that we need cosine x to equal negative root 2 over 2, and we need x to be between 0 and pi, because that's the restriction for the cosine function. So if you're thinking, oh, well, I could just do the same trick as up here and just say, well, if cosine inverse of positive 1 over root 2 is pi over 4, then cosine inverse of negative 1 over root 2 should be negative pi over 4. And that's actually not true, because cosine of negative pi over 4 is positive root 2 over 2, right? So it's trickier than that. So we have to think through this, right? The value that will do the trick is going to be 3 pi over 4. Okay? So cosine of 3 pi over 4 is negative root 2 over 2, and 3 pi over 4 is within this interval. So anyway, negative pi over 4 wouldn't work for two reasons. Number one, because cosine of negative pi over 4 is not negative 1 over root 2, it's positive 1 over root 2. But second of all, negative pi over 4 doesn't live in this interval. Okay? So 3 pi over 4 is the one that you want for the cosine function. Okay, let me give you one more. This one's a little different. Let's say that you wanted to figure out what secant of sine inverse of negative 3/4 is. Notice that an inverse trig function is going to take a real number and it's going to spit out an angle. And then you're going to be taking secant of that angle. So this statement or this expression makes sense. It's not like it's a self-contradictory expression or anything like that. But it is a little bit like, man, where do we even get started? So here's what I would suggest. For problems like this, since you know that an inverse trig function returns an angle, you can just call it theta, right? So in other words, theta equals sine inverse of negative 3/4. Now what does that mean? That means that sine theta equals negative 3/4, and that theta is between negative pi over 2 and pi over 2. Okay, so we can draw a picture of this. Pictures are really useful on these particular problems. Okay, sine theta is negative, right? That means that theta must be in quadrant 4. Remember, all students take calculus or whatever. Sine is positive in quadrants 1 and 2. That means it's negative in quadrants 3 and 4. But since theta has to be between negative pi over 2 and pi over 2, right? Negative pi over 2 and pi over 2, that means theta must be in quadrant 4. And it's not this angle, it's not this positive angle, it's this negative angle right here. Right? That's theta. Now, we can draw a little right triangle. we can say sine theta is negative 3/4. That's negative 3, right? Opposite over 4, hypotenuse, right? Opposite over hypotenuse, negative 3/4. And then we can solve for x, right? Because secant is hypotenuse over adjacent, right? So it's r over x. So we need to solve for x. But we can do that using Pythagorean theorem, right? We can say x squared plus y squared equals r squared. In other words, x squared plus 9 is 16. So x squared is 7. No. Yeah, 7. Holy schmoly, man. Subtraction. It gets me every time. Anyway, x is plus or minus root 7. So you have to make a decision. Is it the positive square root of 7 or the negative square root of 7? And thankfully, because of this picture that we've drawn, you can tell that it's going to be the positive square root of 7. Right? Because x is positive over here. X is negative over there. Right? X is positive root 7. So that means secant of sine inverse of negative 3/4 is the same thing as secant theta, because we called sine inverse of negative 3/4 theta, right? And secant theta is hypotenuse over adjacent, so 4 over root 7. Or if you prefer to rationalize it, you can say that's 4 root 7 over 7. Okay. So that's how you take care of something along those lines. Let's do some more examples. So let's just make sure that you know how to use your calculator. So use a calculator to approximate tangent inverse of 0.7. Go ahead and give the video a pause. See if you can figure out how to use your calculator to do that. You should have a tangent inverse button somewhere. Make sure you're in radian mode, or else it's going to spit out an answer in degrees. You want an answer in radians. Okay, so tangent inverse of 0.7, you should be getting that this is approximately 0.610726. And it probably goes on and on and on forever. It's an irrational number. Okay, that's that. Let's tie this back to calculus a little bit and calculate some limits. So let's do limit as x approaches infinity of secant inverse of x. Okay. There are a couple of ways that you could go about doing this. One way that you could do this would be to just plug in bigger and bigger and bigger values for x and see where see if secant inverse is approaching some finite value, or if it's maybe going off to positive infinity or negative infinity or something like that. So one way to do it is to make a table of values. Another way to do it would be to think about what the graph of secant inverse of x looks like. And we just took a look at it together a second ago. Let's see if we can recreate it from memory. So I know that the restriction for the secant function in order to define the inverse is that you're going to be between 0 and pi, except that at pi over 2 you have a vertical asymptote. Well, so the inverse is sort of tipped over on its side. And so if you have a vertical asymptote on at pi over 2 for the secant function, that means you have a horizontal asymptote at pi over 2 for the secant inverse function. I'm going to call this pi over 2. Pi over 2. And I know that I've got a horizontal asymptote there. I also know that the secant function goes through 0, 1. That means that the secant inverse function goes to the point 1, 0. So if I call this 1, then I've got that point on there. And let's see. So I also know that the secant function goes to the point pi negative 1. Yeah, pi negative 1. That means the secant inverse function goes to the point negative 1 pi. So that's pi over 2, then maybe pi is up here. Okay, so it goes through that point. And since this is a horizontal asymptote, the picture we get should look something like this for the secant inverse function, right? So that's what the secant inverse function looks like. Well, so now we can answer the question pretty easily because we've got a graph right in front of us. What's happening as x goes to infinity? F of x is approaching pi over 2. So secant inverse, limit as x approaches infinity of secant inverse of x should be equal to pi over 2. Pretty obviously. Again, you can make a table of values to kind of verify that that's the case. Let me give you another example. So we'll do limit as x approaches infinity of cosine inverse of x squared plus 2x plus 5 over 2x squared minus 7. Now, because the trig functions are continuous, and because inverse functions are continuous if the parent functions are, cosine inverse, or the inverse trig functions in general, are also continuous on their domains. And so what that means is that we can take this limit and just put it inside of here. So we're really looking for cosine inverse of limit as x approaches infinity of this thing. So if we can find limit as x approaches infinity of this rational expression, then we can just plug that value into the cosine inverse, okay? So in other words, I'm thinking of this. Cosine inverse of limit as x goes to infinity of this expression. Now, in order to not have to write down so many steps, let me just point out that this is a rational expression, and as we've discussed, the limit as x approaches infinity of rational expressions boils down to what's happening with their leading terms, right? So really this is the same as x squared over 2x squared. Right? The rest of it is negligible. It's not going to really contribute much when x is really, really large. Okay? So, and now the benefit of doing that is that the x squareds cancel. So this is really cosine inverse of the limit as x approaches infinity of 1/2. Well, 1/2 isn't dependent on x. So as x goes to infinity, 1/2 is just going to still be 1/2. So really this is just cosine inverse of 1/2. Which I think we just did, didn't we? Oh no, we did 1 over root 2. So let's think about it. Cosine inverse of 1/2. That should be pi over 3. It should be pi over 3. Okay, let's do one more. Let's do limit as x approaches infinity of cosine of 2 times tangent inverse of x. Oh, what do I do here? Let's see. Again, cosine is continuous, so I can just distribute the limit inside of here. So I can really think of it like cosine of 2 times the limit as x approaches infinity of tangent inverse of x. Now, to figure out what the limit as x approaches infinity of tangent inverse of x is, we could draw a picture the same way that we did for the secant inverse function. Tangent inverse is restricted between negative pi over 2 and pi over 2. It has asymptotes there. So if I call this pi over 2 and negative pi over 2, then I've got a couple of so the tangent function has vertical asymptotes at these places. So the inverse tangent function has horizontal asymptotes at those places, right? I also know that the point 0, 0 is on the tangent function, so therefore the point 0, 0 is on the inverse tangent function. That's maybe not terribly helpful. I also know that pi over 4, 1 is on the tangent function. So that means 1 pi over 4 is on the tangent inverse function, so that point right there. And in a similar way, -1, negative pi over 4 is going to be on the inverse tangent function. So this is the picture we end up with. Something like that. So what's happening as x goes to infinity? It looks like tangent inverse of x is approaching pi over 2. So this should be cosine of 2 times pi over 2. That's just cosine of pi. Cosine of pi is -1. Okay? So that's how we deal with those kinds of limits. Here's another way we can tie these concepts to calculus. So let's determine where the function is continuous. So let's do this for f of x equals sine inverse of 1 over x over x. Okay. Well, sine inverse is continuous on its entire domain. The domain of sine inverse. Oh goodness, what is the domain of sine inverse? So the range of the sine function is -1 to 1. So the domain of the sine inverse function is -1 to 1. So sine inverse is continuous on the interval from -1 to 1, but 1 over x is undefined when x is 0. And not only that, but the overall function is going to be undefined when x is 0 because of that 0 right there. So where is this function continuous? It's continuous on the interval from -1 to +1 except for 0. Yeah. So, well, actually, is that right though? I don't know if that's quite right, because sine inverse is sine inverse of x has a domain of -1 to 1, but you could plug in values of x that make this input value, like you could plug in, for example, 2, or you could plug in 10,000, and this value would still be between -1 and 1. So what can't you plug in? You can't plug in something like 1/2, because if you plugged in 1/2 for x, then you'd get 1 over 1/2, which would be 2, and sine inverse of 2 is undefined. So actually, you need for x to be bigger than or equal to 1, or less than or equal to -1. That's really what you need. Because then that way 1 over x is going to be between -1 and +1. So how could we write this down? We could say something like this. We could say we need for 1 over x to be less than or equal to +1, and we need for 1 over x to be greater than or equal to -1, right? So if you solve for x, you can flip the inequality. If you flip the rational expression, then you have to flip this inequality, right? And same thing over here. So the logic is kind of a little bit tricky perhaps, but yeah, we would need for x to be bigger than or equal to 1, or x to be less than or equal to -1. We also need for x to not be 0, but notice that if x is bigger than 1 or less than -1, it's not going to be 0 anyway. It's like this is the, so if we're looking at the number line, this is the this is where the function is continuous. Right, that's where the function is continuous. So 0, is already not going to be included there. So, okay, so where is the function continuous? It's continuous on -infinity to -1, union 1 to infinity. Right, that's where it's continuous. Whew, that was trickier than I expected. I was looking at it like, this is easy. No, that was a little bit tricky. But there you go. That's where the function is continuous. Let's do another one. Okay, where is the function continuous? Let's do f of x equals secant inverse of x over pi plus 4 tangent inverse of x. Okay. So where is that thing continuous? Well, in the first place, we need, so secant inverse of x, we drew a picture of it a second ago, right? The domain of this thing is all reals except for the space between -1 and +1. So automatically that gives us one domain restriction, right? So that gives us one set of numbers where the function is discontinuous, I guess you could say. I mean, it's continuous on its domain, but its domain is all reals except for -1 to 1, right? So it's discontinuous between -1 and +1. What about tangent inverse? Tangent inverse is continuous on all the real numbers. However, we do need for pi plus 4 times tangent inverse of x to not be 0. So let's make sure that that doesn't happen. So that means tangent inverse of x cannot be, well, if I subtract pi and then divide by 4, we get -pi/4. So tangent inverse of x cannot be equal to -pi/4. Ooh, and we just talked about that too, right? Like, wasn't this -pi/4? That means x can't be -1. Right? X can't be -1. Interesting, right? So this thing is continuous on all of the reals except for the numbers between -1 and 1, including -1. So here's what this would look like. So it's continuous from -infinity to -1, not including at -1, and then it's continuous from 1 to infinity. This time it can include the +1. Okay, so very interesting, very interesting function there. Okay, I have one more for you before we call it. Let's do f of x equals cosine inverse of the square root of 2x. So where is this function continuous? Okay, so two things need to happen. First of all, we need for the square root of 2x to be between -1 and 1, because that's where cosine inverse is defined, right? We need the argument to be between -1 and 1. So we need this to be true. We also need for 2x to be positive, or, at least 0. Because if 2x is negative, then the square root of 2x is not a real number. So we need both of these conditions to be met. This one's easy. We need x to be bigger than or equal to 0. As for this one, Well, here's what I'll say. If x has to be bigger than or equal to 0, then certainly square root of 2x needs to be bigger than or equal to 0. So I'm going to replace the negative 1 with a 0. And then if we square both sides, we get this inequality. And then if we divide by 2, we get that. So x has to be between 0 and 1/2. So x has to be bigger than 0, but less than 1/2. That's interesting. Less than 1/2, huh? Because what would happen if you plugged in something bigger than 1/2? If you plugged in like 1, 2 times 1 is 2, and the square root of 2 is bigger than 1. Yeah. So x, that's absolutely right. Yep. X has to be smaller than 1/2, or equal to. It could be equal to 1/2, right? 2 times 1/2 is 1, and the square root of 1 is 1. So it could be equal to 1/2, and it could be equal to 0, but it has to be somewhere. It has to be between those values. Okay, so there you go. So this function is continuous from 0 to 1/2. Very interesting. Okay, so that's that. That's how continuity works for these things, and that's all I have to say for now.